All right, we'll get started. So homework number 4 again is due on Tuesday. Okay, and classroom surface disinfection today for Nathaniel and Jared. Okay, let's get started. Last time we start this chapter and then we give definition for the force. So it's either push or pull. It's a vector quantity. So then you want to specify the magnitude as well as the direction, okay? And then we also talk about free body diagram. That's something you wanted to do when you are studying dynamics of the object. So you always want to indicate or draw all the forces, external forces on the object that is moving. Okay, that's free body diagram. So for vector notations of force, so we actually talked about this earlier in a previous chapter. So you can use the x and y component. You can use it in this way. So A will be the x component times I. That's in the I direction plus B times J. Okay, so that's y direction. Or in 3-dimensional, then it's expressed in IJK or XYZ. Okay. So if there are multiple forces on the object, you want to add them up. So you can either say net force using this notation, force with a subscript of net, that means net force, or you can say summation of all the forces, okay? So then you add all the forces up to be acting on the object. And we talk about Newton's first law of motion, which is also called law of inertia. So simply can be expressed in this mathematical expression here. If velocity is equal to constant, so it could be 0 or it could be a constant number with the same direction, then net force will be 0. Okay, so if net force is not 0, then velocity will be changing. Okay, so that's basically first law of motion says. And you will realize if the velocity is changing, then there's acceleration. Okay, so then that leads us to the Newton's second law, which simply says the force on the object, or the net force on the object, to be more specific, should be equal to the mass times acceleration. Okay, so this is basically Newton's second law of motion put into equation. Net force equal to mass times acceleration. All right. So that's what we learned last time. All right. Today we are going to expand this Newton's second law of motion into 3 components. Okay. So then simply you are writing this equation in components form. So this is the vector form, okay, where you say the summation of force, or in vector form, that should be equal to mass times acceleration, which is a vector. Now, if you take the components, then net force in x direction, okay, then it's going to be equal to mass times acceleration in x direction. And then y direction net force should be equal to mass times the y directional acceleration, all right? Similarly, if there's a third dimension, a z dimension, then net force in z direction is equal to mass times acceleration in z direction, okay? All right, so let's take a look on this exercise here. So this is a 2-dimensional problem. So you will just have I and J here. It says find the acceleration of the body which has mass of 5.0 kilograms, shown in the figure below. Okay. So you are going to do the x direction and then the y direction. Okay. And then it says acceleration. So you can put it in 2 ways. You can use the x and y components, express the a acceleration equal to ax times I plus ay times j. Okay. You need to solve for ax and ay. Or you can do the component method. You can, or you can do the magnitude and direction. Okay. So either way, give it a try, and then you can submit your answers by clicking on the problem here. Okay, so I think most of you guys have submitted your answers. We can take a look here together. You're looking for oscillation. Okay, so according to second law, that should be equal to net force divided by the mass. Okay, from the free body diagram, there's a force of 10 going to the positive, and then the force of 2 newtons going to the negative. There's a 4 Newton force going in that direction. Okay, so this is the I direction, this is the J direction. Okay, so your net force, if you can figure out your net force, then you can figure out your oscillation. Okay, so net force equals to 10, and then 2 is in the opposite direction, so that will be 8 newtons. Okay, in the I direction, and then plus this is negative 4, so minus 4 newtons in J direction. Okay. So then you can do this way, put the net force in the format of I and J, the two components. You can solve for your oscillation. Oscillation should be 8 newtons I plus or minus, let me do minus 4 newtons J divided by the 5 kilogram. Okay, so then should be 8 over 5 minus 4 over 5. Okay, so which will be 1.6, or you can keep the 8 over 5. So newtons over kilogram, that will give you meters per second square. Okay, so you can keep the units at the end. Okay, so let's put the units at the end here. So 1.6 I minus 0.8 J meters per second square. Okay, so I see a couple of you guys get that one right. Okay, all right. So come here. All right, and I figured 1.8 is probably the magnitude, okay, if you did that. But if you just calculate the magnitude, you also want to specify the direction, okay? So it's on that one. Questions you might have? Okay. I think last time I forgot to, during some time of the class, forgot to put the camera back to the screen. Okay. Yeah, also I think I forgot to turn on the PowerPoint slides yesterday. I thought I did, but this morning I found I didn't. Okay, so in the future, if you guys notice that the PowerPoint slide is not send me an email, then I can turn it on. Okay, so it's, but you can also easily access it. For example, today's we are having the 16th. Okay, so they are actually all up online. I just didn't turn it on so you guys can see. So today is the 16th lecture, so the next one will be 17. Okay, you can try that. It's already online. Yeah, but I need to turn it on Moodle for you guys to see. Okay. All right. All right. So you guys are most familiar with the expression of net force equal to m times a. All right. But basically, when Newton first proposed his second law, he didn't write in that expression that we are all familiar with. He actually wrote in this expression. So it's basically net force equal to time derivative of momentum. Okay. So momentum, although we haven't learned about it, but momentum is defined as mass times velocity. Okay. So you can see mass is a scalar quantity, velocity is a vector. So momentum should be also a vector. Okay. So this is what he initially proposed. But we will talk about momentum later in a couple of chapters later. Okay, but this is to just give you an idea when he first proposed it's in this format. Okay, so and then this is more complete description of it. Okay, so because if you take time derivative of momentum here, then you are doing time derivative of m times v. In the case that mass doesn't change, all right, then you are doing derivative of v over t, which gives you acceleration. That's the definition, right? So then net force equal to mass times acceleration. Okay, so in this case, all right. But there's another scenario that your mass might be changing. Okay, a lot of times when you encounter a problem, the mass of the object doesn't change. Okay, but sometimes it does change. For example, when the rocket is going up into the space. Okay, so in that case, the rocket is experiencing the fields all the time. So the mass actually changes. Okay, velocity might change or might not change. It's changing most of the time, but it might not change at a certain moment. So that mass is changing. Okay, so that actually gives the thrust, the force to push the rocket upward. Okay, so that's the main thing when you are sending the rocket into space. It's because mass is changing. That's the main force. Okay, it's not the velocity changing that gives the force. Okay, actually, mass changing gives the force, then changes the velocity. Okay, but this is a more complete description of the second law. Okay, just in case you are wondering. All right, but for right now, we'll just focus on the case that mass is not changing. So then we are still going to use pretty much this equation F equals to mass times derivative of velocity over dt, or mass times acceleration. Okay. All right. Um, So the next section in this chapter talks about mass and weight. Okay. I think you guys probably already know this. So every object near the surface of Earth has weight. Okay, so weight is nothing but it's due to the pulling force of the Earth to the object, which is called gravitational force. Okay, equal to mg, the mass times the g constant. Okay, so it's magnitude. So you can see the weight itself should be a force, should be a vector. Okay, weight has the same direction of gravitational acceleration pointing downward, but the magnitude of it is equal to mass times g. Okay, so weight has a SI unit of Newton. Although we use pounds all the time, but pounds is not a SI unit for force. Okay, but remember pound is a unit for force. Okay, it's not unit for mass. All right, so with that, we can take a look on this practice problem here. It says if you pull upward a stuffed suitcase with a force of 105 newtons and it accelerates upward at 0.725 meters per second square, what are the mass and then the weight of the suitcase? Okay, so first, figure out the mass, and then automatically you use the mass, you can figure out the weight, okay, which is m times g. So try to draw the free body diagram first, okay, and then you'll see how you can solve for this one. So basically, if you draw your free body diagram, you should have all the forces indicate on your suitcase, and then you can figure out what the net force from the free body diagram, and then also from the Newton's second law, you can combine the two, okay? And I think that's pretty much what we had earlier. Okay, so one we had earlier here, this is the free body diagram that's given. Okay, and then from the free body diagram, we can figure out the net force that is equal to AI minus 4J. Okay, and then we are going to utilize the second law, Newton's second law, to figure out acceleration. So you might be following the same procedures on this exercise too. Okay. All right. So I saw several responses there. Unfortunately, I didn't see a lot of correct answers there. Okay, so you guys probably want to listen closely here. So on this one here, let's do the free body diagram. Okay, okay, we can always sketch the problem. So let's see. Let's say this is your shoe case. Something like that. Okay. Now it says you pull it with a force of 105 newtons. Okay, so if you draw your free body diagram, okay, this is the force that's specified by the problem. Okay, but is there any other forces here? Yes, weight. Yes, weight should be always your under your radar of consideration. Okay, so then there should be weight here, right? So there's at least two forces over here. Okay, and then it says it goes up with an acceleration of 0.725 meters per second square goes up. Okay. So in this case, yeah, so you will have two forces on this. Okay. So then looking at this free body diagram, okay, so this is pretty much what you guys are going to do on a problem like this. Okay, when you are dealing with the second law. So first, you have your free body diagram. You indicate all your forces. Then from looking at the free body diagram, you can say my net force, okay, should be, in this case, should be equal to, because those are both in along the vertical direction, okay? So upward and downward. So it's going to be 105 newtons minus mg. That's your net force, okay? That should be just in the y direction, all right? So you can just set up y direction for this guy, for this problem only, okay? You don't need an x direction because the suitcase is not moving in the x direction, all right? And it doesn't, there's not any force in the x direction, okay? So then this should be sufficient, all right? Now, this is from your free body diagram, okay? The second one, you can write out your second law, Newton's second law of motion. So that's mass times acceleration. Okay. So then you will have these two equations. The second one is from the second law of motion. Okay. All right. Now you probably realize that the left-hand side of the equations are the same, right? So then the right-hand side should be equal to each other. So 105 minus mg should be equal to ma. All right. Or if you want, you can put the newtons here for the units. Okay. Now we can examine this equation. See if we have everything we need to solve for the first part A, mass, and then part B, the once we get part A, we will get to part B. Okay. So you can see here, the mass is unknown. G is always 9.8. Okay, and then this guy is given as 7.725. So you can solve for your mass here. Okay, you put the two terms as mass to the one side of equation. So 105 newtons equals to mg plus ma. Move this guy to the other side, minus become positive. Okay, and then you can single out the mass, g plus a, mass times g plus a equals to 105 newtons. So then divide both sides by g plus a will be giving you the mass. Okay, so divide both sides by g plus a. All right, so then you can plug in the numbers. Or 105 is there. G is 9.8 plus 0.725. These two are both in meters per second square. Okay, so that would be 9.976 kilograms, or 9.98 if you keep 3 sig figs. Okay, for part A. Now you have the mass there, so you can solve for your weight. Weight is equal to m times g. Okay, 9.976 kilograms times the 9.8 meters per second square. Okay, so that would be 97.77 newtons, or 97.8 newtons. Okay, all right. So I think looking at the answers here, I kind of get where the 145 is from. It's probably like you divide 105 just by 0.725. That sounds like we'll give you this number, okay? But remember, that's because when you do your free body diagram, you probably just thought about just the pulling force, but forgetting the weight, okay? So if you include weight in your free body diagram, then you should be good if you are getting 145. Okay, and then this is the right here, the right answers here for A and B. Okay, all right, and I'm not quite sure about this set of numbers, but we can refer to the solution, okay, for the correct answers. Any questions you guys might have? Okay. So on weight, there's another term you might see often. It's called apparent weight. Okay, so apparent weight, it's not your actual weight, but it's based on the contact of your body with a surface. For example, if you are standing in an elevator, when the elevator just start to going upward or going down, then the system and your body have acceleration. Okay, so then in that case, your weight doesn't equal to the supporting force. So normally when you stand on the floor here, the floor gives you the force that supporting you. That is the same as your weight. Okay, so then you are not moving vertically at all. Okay, but when you are having acceleration, then mg and the supporting force, they are not equal to each other, because in that scenario, then there's net force on your body. Okay, that gives you acceleration. Otherwise, your acceleration should be 0. Okay, so this is how you feel the gravity. Okay, so normally you don't feel it because there's cancellation of supporting force and your weight. But if the two are different, then you will feel gravity or loss of gravity, or maybe adding on of gravity. Okay, so yeah, so the contact force between your body and your surrounding, so basically it's the floor here. So in this case, if the elevator is going upward with acceleration, then the apparent weight or the supporting force is larger than the actual weight. Then this is the supporting force is called the apparent weight. Okay, so let's take a look. An example with the apparent weight. So it says if you are as part of your physics experiment, you stand on a Boston scale in the elevator. So in that case, you can see your apparent weight. So then in that case, the scale will reach your apparent weight. Okay, if the oscillator is not having an oscillation, then it's your normal weight, right? So if it's oscillating, then your weight is showing on the scale is probably different. Okay, that's your apparent weight. It says normally your weight is 610 newtons. Now, when you are in the elevator that is moving, the scale says 730 newtons. So what would be the acceleration of the elevator? Yeah, in A, it's asking what's the direction of the acceleration, and then in B, it's asking you what's the magnitude. Okay, so basically you're looking for your acceleration, and then C is asking you, can you determine the direction of your velocity or the elevator's velocity? Okay. So you guys can give it a try, and then we can take a look at solutions together in a couple of minutes, okay? Now in this one, although it's looking for the oscillation of the elevator, but you can actually try to figure out your oscillation, okay? Because as you and the elevator share the same oscillation. So then once you determine your oscillation, it will be easier to determine the oscillation of the elevator, because if you are considering the elevator, maybe the scenario may be a little bit more complicated, because there's weight, there's cable pulling the elevator, and then there's you are standing on the elevator. Okay, so many more forces to look for in that scenario. All right, I think let's take a look on this one together. I saw a couple of responses already. You can keep submitting your responses there, okay? So if you, as I mentioned, it might be easier to just look at your body as your object of interest, okay? So then, because the scale reads 730, so that means the supporting force from the scale should be 730 newtons, okay? And then again, you always want to consider the weight of the object, in this case, your body, that should be mg, okay? So similarly, there will be two forces here on your free body diagram, okay? So the dot represent the object of interest, and then two forces there. So this is your normal weight, mg, it's 610 newtons, okay? So you are given two forces, 730 and 610. Now you can see, if you look at the free body diagram, so the net force, again, will be just in the y direction, okay? You just need to focus on the y direction here. That should be 730 newtons minus 610 newtons, okay? It's 120 newtons, that's in the positive y direction, okay? So then net force is in positive y direction, that means your acceleration should be also in positive y direction, right? So in part A, the acceleration should be upward, okay? That's due to the net force is upward, okay? And then because your acceleration is the same acceleration as the elevator should also have this upward acceleration, okay? B is asking what's the magnitude. All right, so this guy is from free body diagram. Then you can look at the Newton's second law of motion, so mass times acceleration. Okay, so you can take, this is 120, so 120 newtons equals to the mass times acceleration. You're looking for acceleration, right? And at this point, we don't know mass, but because it gives you weight, so then that's equivalent to also giving you mass, right? Because mass times g is your weight. If weight is given, then mass is given, okay? So you can, from here, you can solve for your mass should be equal to weight divided by g, okay? 610 newtons divided by 9.8 meters per second square. That would be 62.24 kilograms. All right, so then this is 62.24 kilograms equals to A. So then both sides divide by that 62.24 kilograms to give you your acceleration, okay? So your acceleration will be 1.93 meters per second square. Okay. All right. Now in part C, I think the original two responses I look at has different responses on C. But in here, you only know that acceleration is upward, right? You shouldn't be able to tell what's the direction for velocity, because velocity and acceleration, they do not necessarily share the same direction, okay? So in two scenarios, you would have the acceleration that going up, okay? So if the elevator is going upward and then start to go upward, okay? So in that case, velocity and acceleration are in the same direction, okay? Another scenario is if the elevator is going down and then slows down. In that case, now because it goes down, velocity is going downward, but acceleration is upward. That's how it slows down, right? So in that scenario, you can also have acceleration going upward. Okay, so either way, acceleration velocity could be upward or downward in two scenarios. Okay, so no, that is because acceleration and velocity, they don't share the same direction. Okay, you can just simply say that way. They do not share the same direction, or they do not necessarily share the same direction, okay? In some scenario they do, in some scenario they don't. Okay. All right. Questions you guys might have, if any. Okay. So yeah, I think most of you guys got this one. Yeah, the magnitude right. Okay, so pretty good there. Okay, and we can move on to the next section. So we have talked about Newton's first law and then second law. So in one sense, first law and second law, they are actually all, the first law can be actually described by the second law, because second law says net force equal to mass times acceleration, which means change of velocity over t, right? So in that scenario, you can say if net force is equal to 0, then there shouldn't be any change of velocity. So which is first law, okay? But there's a third law of Newton's motion, okay? So when you see a force, okay? So for example, if you are pushing on the wall, if you go swimming, you are pushing on the wall, then that's how you actually get the force that pushing you, okay? So you can go backward. Or when you are pushing on your table right now, you will probably feel like something is pushing back on you, right? So for each force that you see, there must be a counter force, okay? So if the swimmer here pushes the wall by her feet over here, feet on the wall, there's a force there, then the wall will push back on her feet there, okay? So that's basically Newton's third law. So it says forces always come in pair, acting on different objects. So when you see a force, then you can actually find another counter force of it. Okay, but those two should be acting on different objects. Okay, so there's one force acting on the wall, and then the wall is acting on the exerting the force on the feet here. Okay, so on different objects. And these physics they are called these forces they are called action and reaction pair. Okay, so this is the action and reaction pair. All right, but if you are looking for the free body diagram the swimmer here, you'll see three different forces. Okay, they're acting on the same body, so they are not action and reaction pair at all. Okay, so if the two forces are acting on the same body, then they shouldn't be the action and reaction pair. Okay. So we can look at a few scenarios here to determine which ones are action and reaction pairs. Okay, so let's look at the scenario that if you have an object on a scale, put the camera on the screen. So let's see. So then if you look at the this guy here, okay, so let me see. So this is the S is the contact force between the object and the scale. Okay. All right, so it says Newton's first law pair and then Newton's third law pair. Okay. Yeah, so if two forces are action and reaction forces, then sometimes they are called Newton's third law pair. Okay. If two forces they cancel out each other acting on the same object, they are sometimes called first law pair. Okay. So if you see that, but basically you can see here on the object here, these two forces are acting on the same object, right? They cancel out. So that's the first law pair. Okay. For the third law pair here, so this guy, the force on supporting force on the object, and then the force by the object on the scale. Okay, these two are third law pair or action and reaction pair because they are the same magnitude in opposite direction and then acting on different objects. Okay, one is acting on the box, and then one is acting on the scale. Okay. Also, on the scale here, there should be its weight, and then oh, let me see. This guy, the weight. Let's look at this pair first. Okay, for the object, this is referring to the object. Okay, so there's the weight, okay, of itself, and then because of the interaction between the object and the Earth, so the Earth is pulling the object downward with its weight. Okay, but at the same time, actually, the object is pulling the Earth upward. Okay, with the same amount of force, but in the opposite direction. So this is the pulling force of the object on the Earth. Okay, so it's very small if you are talking about the Earth itself. Okay, but there's that force as well. Okay, so that would be according to Newton's universal gravitational law, which we haven't talked about. Okay, but just keep in mind the Earth is pulling you downward. At the same time, you are pulling the Earth upward. Okay, although you wouldn't make it move at all because the Earth is too big. Okay. All right. Now I don't think. Okay. And then so then this and this guy. So this would be the pulling force on the Earth by the object. Okay. And then this is the where the scale is given to the Earth. Okay. So then these two are acting on the Earth at the same time, and then they cancel out. So that's a first law pair. Okay. Another scenario here, if a professor is pushing a cart in a classroom, you can find a couple pair of action and reaction forces. Okay, so when she pushes on the car, giving the car a force called F sub pro. Now at the same time, the car is pushing her back with F sub car. So these two are action and reaction pairs because they are acting on different objects. Okay, and then having the same magnitude. When she's walking, she actually pushes the floor backward. At the same time, the floor is pushing her forward. Okay, so these two are a pair of action and reaction forces. Okay, or the third law pair. Okay. All right. So then, on the action and reaction pair force, we will take a look on this system here. So you have two objects that has in contact. Okay. You apply a force on the lighter object here, then the force is going to push the two boxes going in that direction, right? Now there should be net force on this system of two objects because they will share the same velocity and acceleration. So we can treat them as one system first, okay? So they will move in that way. So it's asking you what would be the contact force between this one and that one, between the two boxes, okay? Now, due to the time limit, I think I'm going to just show you guys the solutions here, okay? All right. So when you have two objects in a problem, okay? So if they are moving together, then you can actually treat them as one system first, okay? And then later on, when you are looking for their interaction forces or their contact force, you will separate them, okay? So this is what you will have to do on a system of two objects together. So first, you want to treat them as one system. Okay, or you can say treat them as one object. So then there's pulling force there. There'll be weight of the box. Which one is one? This is one. There will be weight of the second one. There will be supporting force on the first one and then supporting force on the second one. Okay. Now, these are all external forces. If you look at the force between box 1 and 2, so because you treat them as one system, then the forces between 1 and 2, they're actually internal forces. Okay, so for the free body diagram, if you treat them as one system, then you don't have to indicate those internal forces. But then later on, you can treat them separately. Okay, so you can look at box 1. So there will be weight of it, and then there will be normal force. Okay, now there will be a force by 2 pushing on 1 in that direction. Okay, so F of 2, 1. That means force by 2 acting on 1. So this is box 1. All the forces on box 1. Okay, on box 2, let's list external force F, because that force is acting on 2. Okay, now there will be less contact force by 1 on 2, because if 2 is pushing on 1, then 1 will be pushing back on 2. Okay, so F of 2 on 1, that will be its weight. That will be the normal force. Okay, so then if you can see that when you treat them as one system, you do not include the external forces. When you treat them separately, then external internal forces show up as external forces on each of them. Okay, each of the object there. All right. Now, if we treat them as one system, to do that, then we can figure out what will be the oscillation of the system, right? Because the two boxes, they share the same oscillation, all right? And then once you have figured out that same oscillation, then you can use the same oscillation for box 1 and box 2, because those two have the same oscillation, okay? So let's treat them as one system. First, looking at the free body diagram over here, you can see the supporting force will cancel out the weight on 2 and then also on 1, okay? Because it's not moving. So then net force should be just equal to this F, okay? Now from this Newton's second law, you should be able to figure out net force equal to mass times acceleration. But in this case, because you treat the two boxes together, so it's the total mass, okay? Which means M1 plus M2. So then you can set up that the pushing force equal to the total mass times acceleration. So this is the total mass. All right. So then you can solve for your acceleration. It will be F divided by M1 plus M2. It gives you F as 5.0 newtons. F1 is 5.2 plus 7.4. Okay. Let me have a double check on the numbers. 5.2 and 7.4. Okay. They are both in kilograms. So Newton over a kilogram will give you meters per second squared. Okay. So that's your oscillation. All right. Once you have your oscillation, then you are going to treat them separately to figure out the contact force. Okay. So this one and this one, they are actually a reaction pair, so they should have the same magnitude, but just in opposite direction. So you can either figure out this one or that one. Okay, it will be the same. It looks like it might be easier to figure the force by looking at box A, because there are only 3 forces here, and then this one cancel out that one. Net force will be just that guy. Okay, this guy will cancel out that. Net force will be equal to combination of these two. A little bit more complicated. Okay, so should be easier to solve for the contact force by looking at this one. Okay, so net force on box 1 is equal to F2 on 1. Net force on box 1, you can apply Newton's second law of motion. So net force of 1 should be equal to m1 times acceleration of 1. Okay, but because they share the same acceleration, so it's the same. So combining these two, again, this is from free body diagram. Okay, this is from the second law. Similarly on here, this is the free body diagram. This is the second law, okay? Two equations. So then you can figure that F21 should be equal to M1 times acceleration. Okay, so 7.4 kilograms times 0.397 meters per second square. Okay, that gives you 2.9 newtons, 2.94 or 2.9, keep 2.6 fixed. Okay. Quickly on part B, if you are applying force in the other direction, okay. So on part B, again, you are going to follow the procedure, treat them as one system. So then force is acting on the other direction. Okay, so force will be in that direction on part B. All right, so acceleration is going to be the same on part B with this magnitude, but direction should be in the right. Okay, so then here, now if you have force on this guy, then the force is in this direction. Okay, so then this doesn't appear there. So then in that scenario, you'll be looking at the second object to solve for the contact force, okay, which will be more convenient because there's only one force on that guy, okay. So then on B, F21 should be equal to M2 times acceleration, 5.2 kilogram times 0.397 meters per second square, which would be 2.1 roughly, okay. So if you follow the steps, you'll figure that way, okay? Figure the answer out at the end. So you'll see that if force are applied on different objects, then contact force will be different, okay? So you don't get the same contact force then. It depends on which object you are applying your external force, okay? All right, so we'll stop here for today and see you guys on Monday.